Hello, as you may know from some of my previous videos, I've been making this little pick and place machine to assemble PCBs, and it's getting to the point where it's starting to be reasonably functional. So I've ordered some bare boards to experiment with and some solder paste and stencils and the parts and everything, but I'm starting to realize that there may come a time that I assemble a board and find myself standing here like a witless moron with no way to reflow the board or solder the parts onto it. So this video is about trying to make a hot plate for doing that, and I wanted to make it nicely controllable with the Raspberry Pi interface and stuff, so that's what I did, but as we'll see, it didn't really work out how I'd imagined. Here are the components that I bought to do this. These things are called cartridge heaters, and they run on mains voltage, so we have to be a little bit careful with this stuff. And then I have a thermocouple to measure high temperatures, and a thermocouple amplifier, which is basically just an ADC that's very sensitive in certain ways, and it also has a little bit of error checking, so it can check that, for example, if your thermocouple is not connected properly here, it will give you a fault condition. And this runs on SPI, so that was fairly easy to set up with the Raspberry Pi. Now unfortunately this particular breakout board is kind of trash. You can see that there's just one little cap on there, and even from a basic reading of the datasheet you can already tell that is not going to be sufficient. And I got to say, this has been without doubt the single most annoying sensor I've ever had to deal with in all of the years of doing Arduino and electronics. And I think part of the reason is because this is just a shitty implementation of it. So do not buy this one, because you'll find yourself having to modify it to be a little bit more like this, which is what I ended up doing. So this costs a little bit more, but look at all the extra stuff they've put on there to save you from stress and having to deal with noise and voltage spikes and all that kind of stuff. Now I don't have one of these, but I would thoroughly recommend you just get this one instead of the shitty one off AliExpress. And then I also bought this solid state relay, which is supposed to be a way to vary the voltage from a mains input. So instead of having the whole 240 volts, maybe you just let half of that through or something. And it's got an input on the bottom here that says 0 to 10 volts, and it says linear proportional, which kind of leads you to believe that maybe you get some sort of a linear range of voltage coming through based on your input, but it is anything but. So if I was doing this again, I don't think I would even bother buying this. It turns out that nothing happens until about 4 volts is showing up on between these two bits, and when you get to about 7 volts, from 7 to 10, it's just fully on. So the range that you get a variable voltage at is rather small and not really that useful. Plus, there's a lot of thermal inertia in the thing that we're heating up, especially for a hot plate, but even for an oven, I think, as well. And so when you change the input, the voltage input, the change in temperature is very, very slow, and there's just not really much advantage to be gained from having a variable input versus just turning the voltage off and then on again completely. So for that reason, this proved to be not particularly useful, and I don't see myself using this at all going forwards. So my plan was to use some of this 6mm aluminium plate that I have so much of and cut some nice little circular grooves out of there with my ball nose end mill and place the cartridges in. I made 2 pieces exactly the same like this, and they were going to fit together like this, and we'd have a nice chunky piece of aluminium, and the idea with that is that the heat would spread nicely and evenly. As it turned out, this was just way too much aluminium, but anyway, I'll show you a little bit of some clips from the live stream where I started making this last week. Okay, I've set this up to do a little test. Mainly I want to see how quickly it heats up and what the distribution of heat is within that plate. So I've just got the ends of each of those connected to the live and the neutral, and then the ground is clamped onto the bottom of the plate, and it's just going into these, and I'm just going to plug this directly in to the mains for now. Now of course we need to check that everything is okay before we plug this in. So each one of these cartridge heaters is about 300 ohms, pretty close to 300 actually. So with 4 of them in parallel we should expect to see 75 ohms or so between the live and the neutral, which is what we've got. And then between the neutral and the ground we should expect to see nothing. And between the, oh well that was live, between the live and the ground, the neutral and the ground, each of those should be nothing. And then between the ground and the plate we should see a good connection there. What's that? 0.3 ohms. So it may seem a bit pedantic to check this over and over. That's like the 4th time I've checked it. But I'd hate to think that anyone would watch this video and then do what I'm doing without fully recognizing the importance of checking everything before you plug it into the mains. The Summer Symphony's going full blast out there. 3 million trillion crickets. Okay, I'm going to plug this in and see what happens. It's just sitting on some stones from the driveway under there. Should be alright. It's a little bit dark, but it doesn't really matter because we're only interested in the thermal radiation from it, which I'm going to look at with this little infrared thermal camera there. Unfortunately, because it's aluminium, I already tried this. I had a little look through there, and all I can see is my own self reflected back in the surface of the aluminium. So I'm just going to put this piece of paper on top of it like that, and hopefully the heat will come through the paper nicely without scorching it too much, and we'll be able to see the distribution of heat coming through there without having the problem of reflection. And you can definitely see 4 distinct spots. Oh, one of them looks... Okay, what does it say there? Oh, it's only 35 degrees though. Okay, I'm going to unplug it there. So I guess maybe it's not coming through the paper very well. Oh, the paper's kind of curled. That didn't really help, did it? Look. See how my hand's reflecting? This is really difficult to measure. I might need to get my my thermocouple or something. I made a little QT app so that we can read the thermocouple and control some outputs. And it's intended for a little touch screen that I have. That's why the buttons are so large there. The thermocouple IC itself actually has a temperature sensor in it as well. That's what this ambient one is. And then the one labeled sensor is the thermocouple itself. Then we have 1 PWM output and 3 digital outputs. And the temperatures that we're looking at here are just dummy values because I'm running this on my desktop computer, so that there's no actual hardware. When you're on the Raspberry Pi, obviously, that you get real numbers. So you can create a profile like this and select it. And on the graph here we see the blue line shows the target temperature at each point along the Reflow profile, and the time and the temperature for that are on the bottom and the left. And the green line, which is moving across slightly there, you can see that is the current live values. Like I say, that's just dummy values, 30 degrees at the moment. And then when we click on this start button, the green line is kind of copied into this red line down here as we go across, and we can keep a history of what the temperature was at each point along the way. The numbers at the top and the right are for the green line. So we have the green line shows you the last 60 seconds of live input readings from the sensor. Alright, here we go, plugging in. Wow, it takes a long time to do anything. What the hell? I could warm it up with my fingers quicker than that. Well, man, it's slow. 48, 49, 50 unplugged. We'll see how far above 50 does it go with no actual extra energy being put in. 66, yeah. Alright, extra 16 degrees. Alright, I'll plug it back in then. 3, 4, 5. Okay, unplugged. Just want to test my theory that there's like 15 degrees still. So it's going to round off at about 100. Huh. Interesting that there was another 15 degrees again. Oops, something's smoking. Okay, unplug. Alright, there's a little bit of smoke coming from... Yeah, it's cooling too slowly. Wow. Let me go and get my floor fan, and we'll see how much difference it makes to be blowing some air across this. Okay, it should be... That's a decent breeze. Oh, it made a difference there. I can... Wow, I'm holding my hand like... Oh, yeah, that's quite effective. Nah, still too slow, isn't it? I'm going to put a big piece of aluminium on top of it and see what that does. There we go. This is 5mm thick. Decent size. Man, it's been like almost another 10 minutes and it's still at 62 degrees. And this is with that large piece of aluminium on there still. And the large piece of aluminium is so hot that I can barely touch it. I think I could probably just touch it for long enough to pick it up and take it away. But I wouldn't want to hold it in my hand. Man, there's so much energy in there. That's incredible. I think there's just too much aluminium in that hot plate. So I bought this multi-plug thing the other day, and I was hoping that I could use these USB outputs here to run the Raspberry Pi off. It says there output max 3.4 amps, but I think that might be a bit bullshit, or it might be that it's 3.4 shared between all of them, because when I tried to run the Raspberry Pi off that just before, it ran, but the red light was blinking a lot, which means that there's bad power. And also you can see these green spikes spiking up. It's actually still doing it now. See how it says fault? The 999 is a value that I told it to report when there's a fault. But it just means that there's a bad... I'm not exactly sure what's going on, but it means that there's something wrong with this. This is not reporting values properly. And it was doing that a lot when I was running it off that USB outlet with the bad power. Now that I'm using this is an actual Raspberry Pi adapter, so it should be alright, and the red light is fine. But it's still giving me these faults every now and then. And I was experimenting indoors, like at my desk with this. I wasn't getting any faults there at all, and what I discovered is that the reason I was not getting faults there is because I had my logic analyzer connected to some of the other pins where I was checking what the PWM output was doing, and the logic analyzer was connected to the computer, which is connected to ground. I'm assuming it's something like that. So for whatever reason, we're getting these faults now, which is really annoying. But what I'm going to do now is I'm going to connect the ground coming out of here to the ground on there, which will connect this to ground, which means this will be connected to ground, like the earth connection of the mains. And hopefully that doesn't damage the Raspberry Pi. I wonder if it might fix this problem too. Probably not, but let's give it a try. Well, unfortunately, it doesn't look like that's going to work. So you can see we're getting the occasional fault when it spikes up to the top there. The green lines this is. But when I ground the hot plate, or the thermocouple, it's the same thing, when I ground that to the mains ground, this is what happens. So okay, I've connected it there now. And you can see it's just going fault, 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 fault. It's just faulting the whole time. It becomes completely useless. And when I let it go, so I let it go now, it goes back to being more or less okay, but it still faults occasionally, even when it's not grounded. So that kind of sucks because I don't want to run this without having the hot plate grounded properly. So it looks like I'm going to have to run this off battery. I thought I might be able to get away with using this 12 volt power supply going into the 5 volt step down thingy and powering the Pi from that, but sadly that doesn't work either. We're still getting some faults every now and then. Not many, but enough to make it not viable, so that kind of sucks. Looks like we're going to have to run this thing on battery. Okay, it's the next day now. I had a bit of a think about this overnight, and I'm starting to wonder if maybe hot plate's not really the best thing to be using if you want a nicely controlled temperature ramp that's going to cool down quickly. The heating up is not a problem, it's the cooling down is the only issue. And yeah, you could take the board off the plate, but even if you do that, the plate's going to be so hot that you couldn't really start another job for quite a long time afterwards, so it would be nice if we could cool it down properly. But anyway, so first step obviously is to reduce the mass of it. So I changed my design and came up with new toolpaths for my CNC routing, and I've done the bottom piece here. I left a bit in the middle because I have a large CPU cooler thingy that I bought years ago that I haven't used for anything, so I'm going to try sticking that on the bottom, see if that helps. Basically all these bits that I cut out here, but we're not going to cut them all the way through, we're going to cut halfway through, so it's going to be 3mm thick still on the main plate part. One of these was smoking when it got up to about 220 or so degrees. It's got a bit of a scorch mark on there. I'm not sure if that's a bad sign or not, but I'm going to keep using it and hopefully it's alright. The other one's looking perfectly fine. Okay, here's the second plate all finished, looking nice and fancy. It's just the same on top, of course. And this is the CPU cooler that I've got. I actually bought this a few years ago for my high altitude balloon project. I was going to make a freezer using some Peltier elements all stacked up together, but at the end of the stack you need to get rid of the heat. So that's what I was going to use this for, but I ended up just using my regular freezer to do some tests with, and that was good enough. And this has been sitting around for quite a few years unused. I really don't think it's going to help a whole lot, but since I have it, I will give it a try and see if it does anything useful. So on this bit here, I've left a couple of holes there to mount that match that. Okay, here we are at night again. Much slimmed down plate. And I've been having a lot of trouble with this thermocouple, or maybe it's the thermocouple IC. I don't really know what's going on, but after I took it inside to work on it a little bit more, it just hasn't been the same. And I've tried 2 different thermocouples and 2 different ICs, like the little chips that, you know, send you the information. And if I get anywhere near it, like I didn't touch anything there, right? It dropped 2.5 degrees just by waving my hand around near the screen. See? How can you fix that? This is the most frustrating sensor I've ever had to deal with. It's so annoying. It's running on battery now. I can't get anywhere near it without... See? See? I'm not touching it. Why is this? It's almost like it's... I don't know. What's going on? If I touch the screen... See? If I touch the screen, it does it too. If I touch the Raspberry Pi, what happens? Nothing. If I touch the shielding of the thermocouple cable, nothing. If I touch the hot plate itself, nothing. So everything that's conductive that you would think, well, a little bit of a bump there even when I wasn't doing anything, everything that's conductive that you would think would cause a voltage change in the system somehow. Touching that is fine, but if I just wave my hand around near the screen, let's see if we can get it to do it again. Yep, there it is. A big one there. God's sake, so annoying! Well, I don't know what the hell is going on with those spikes. I've spent hours and hours and hours trying to figure it out. Just wave my hand, see, wave your hand anywhere near it and you get a spike. I think we're just going to have to ignore it. The trouble is it ruins the graph, right? See if I run this again. Okay, I'm just going to plug the hot plate in. I've had enough of that. Did it even change? Okay, so it did go up a little bit. Wow, it's still very slow, isn't it? Alright, I'm going to plug it in again. Go. Still pretty steady on 1.7 degrees per second. Alright, so pulling the plug here. The best case I've seen so far here is 0.3 seconds, 0.3 degrees per second cooling. But I've read that the best cooling rate is about 4 degrees per second. So we need it to cool 10 times quicker if we're going to leave the board sitting on the hot plate. Okay. That helps a lot. Alright, so it's negative 1.1 degrees per second. So that's about twice as quick. Let me put that that big other big piece of aluminium on. This is why they use conveyor belts, isn't it? Because you want the board to be physically moving out of the hot place. You can't leave it sitting in the hot place. So that's 50 degrees per minute, but we still need to go fast, 4 times that fast almost. Alright, now we have the CPU cooler mounted underneath. I'm not using any thermal paste yet. There's actually a slight gap on one side, so I probably should be using thermal paste eventually, but let's just see how this goes for now and see what, if any, difference this makes. Go. Oh, there we go. Wow, it takes a long time, doesn't it? I think I'll stop it at 100 and see what the overshoot is there. So yesterday, with the full mass of aluminium, the overshoot was only about 15 degrees here. But now it's like 35. So unplugging at 190. Okay, fan is on. Oh, here we go, 0.5 degrees per second, that's not bad. Alright, so this is quite a bit better, but still nowhere near what we need. Alright, we're back to ambient temperature, so let's give this a run again, and this time when I cool it down, I'll turn both the floor fan and the CPU fan on at the same time. Even the heating up is kind of not fast enough. There's a massive wetter just came out of nowhere onto my table from somewhere. Thankfully we don't see many of these. They're pretty disgusting. This one is huge. Hey! Oh, he doesn't care about me. Well, I've been doing a few more experiments today. I changed just a couple of things. I machined off another millimeter or so of aluminium from the bottom of the main flat table part. So it's only about 2, maybe slightly more than 2 millimeters thick there now. And I put some thermal paste in between the CPU cooler and the bottom of the plate. It didn't seem to make a whole lot of difference, so we still have basically the same result. Oh, and despite not changing anything and still running on battery, I'm getting a bunch of spikes now, but they're only happening, you can see it's only happening on the heating side when the temperature's going up. So it's only when the heaters are plugged into the mains that we're getting some spikes now. And yes, I tried grounding the Raspberry Pi to the mains ground, and that didn't help either. That basically just gives you constant faults all the time. So yeah, man, I'm just getting so sick of this.
Oh my goodness.
This thing here, it's just a nightmare, absolute nightmare to try and get that to work properly. Anyway, so you can see that the red line's going up. It doesn't quite go up quick enough at the beginning, but interestingly, just about every time it matches up at the middle there with the blue line right where it's supposed to be, which is kind of interesting. Might be perfectly fine to do that. But as usual, the main problem is just getting things to cool down. So what I've been trying today is I put the floor fan over there so that it's blowing in the same direction as the CPU fan was going that way. That seemed to help a little bit. Interestingly, I found that if I just did not use the CPU fan at all, and I brought the floor fan a little bit closer and I put it up to the fastest speed that it can go, that was actually more useful than having the CPU fan on and the floor fan slightly further away and slower. So it's looking like this fan here is kind of useless. So my next thing that I'm going to try is, I have not tried since I machined all this stuff away. I don't think I've tried it without the CPU fan. So this fan thing here, or the fins and everything, that adds quite a bit of thermal mass as well. So when it's heating up, that's going to slow the heat rate that it can heat up, because all this stuff has to heat up with it. And then when you're trying to cool it down, you need to cool that down with that as well. So you've got more mass overall. So maybe what I should have done is just machined the plate down to be a lot lighter, and then tried that before I put the fan on, but I don't think I did that, so let me try that next. Okay, so we're back to sitting on the rocks again, and before I clear this off, I'll just show you what it was like for that last run. So the time at the bottom there, it's 600 seconds, which is 10 minutes. It's cooled down to 37 or so degrees, which is very comfortable to touch. You could handle it just fine and, you know, pick it up and move it around. And it would be perfectly warm enough or cool enough to put a new board on to start the next job. So the 10-minute turnaround time is actually not too bad. Might actually be perfectly usable like that. But anyway, let's see what we get like this. That's not going to work at all. Okay, so this time I started out with just the plate only sitting on the rocks, and then when it got to the top temperature, I took the rocks away and put it on top of this, and then turned the fan on. And surprisingly, that didn't really help the cooling rate at all. It was still only about 1 degree per second, and it looks like overall it's not going to make a whole lot of difference, at least not much useful difference. It's about the same, so that was a little surprising. So the next thing I'm curious about is, what rate does the temperature decrease of the actual PCB itself if you take it off and put it like over there, for example, at the hottest point? And I've seen people placing thermocouples on PCBs like this with Kapton tape. I'm not sure what temperature they were using them at. I'm planning to go to about 235 degrees, so this tape might not hold up, but hopefully it does. Anyway, let's see what we get with this. Okay, might as well try soldering something since we're doing all this. Put a couple of ICs on this board with some 100-year-old solder paste, so it's not going to do a very good job. But anyway, let's run it and see what we get. 170. Okay, so it's just melted there at 177. Well, one of them did anyway, the other one hasn't. Wow, I'm surprised that... Okay, looks like they're both all completely melted there. It says 198 on the hot plate temperature, so I'll turn it off. Ooh, she's smoking. She's smoking. Okay, so I could pick it up now. It's still pretty warm, but I can handle it alright. So that didn't take long, maybe 20, 30 seconds. A little bit too much solder on there, of course. It actually looks perfectly fine. Well, this was a little unexpected. I connected the light through the SSR here, and it's just going in and out, and the blue is connected to the blue like that, and the input side's not connected to anything, and for some reason I thought this would have no light at all, but when I switch it on, it's kind of like pulsing like that. I thought that, like it says on there, control 0 to 10 volts DC, right? Shouldn't that mean that it's turned off? Surely that's 0 volts, right? Okay, after a bit of Googling I figured that one out. Apparently these SSRs, they don't completely stop the current from going through. There's always a few milliamps going through. And for these LED light bulbs, which is what I was using yesterday, it's enough to allow the light to turn on just a little bit, and then as soon as it turns on, it dissipates the current that it had, or I think there's a little bit of a capacitance in there maybe, and then it dissipates that and turns off, but then it turns on again, so it just repeats that cycle, because these LEDs are so efficient that they can actually turn on with just a tiny little bit of current. So I made a special trip into town to get a regular light bulb, because I don't have any of those anymore in the house. For the last few years I've been replacing them all with these LED ones, so I didn't actually have any normal light bulbs. Wow. Anyway, so we put a normal light bulb in there which has a slight bit of resistance. It's just a normal resistor, and now when I turn this on, we get nothing, which is what I was expecting yesterday. Okay, now I have a 2-cell lithium ion pack, so that's at about 7.3 volts, and that's going through this potentiometer to give us a variable voltage on the input side there, and have my multimeter connected over here so I can see what the voltage is. It's about 0 at the moment, and I noticed that as I turn this around, when we get to about 2.3 volts or so, that light comes on there. Come on, like that. 2.6 volts, 2.5 volts or something it turns on. Anyway, let's turn the mains on as well here. Alright, so that's 0. And hopefully that light will turn on at some point. Okay, oh, it comes on about the same time as that. So, yeah, oh, almost the same time as that. So if I turn it a little bit more, it turns on at 4.3 volts. Oh, so that means with my microcontroller, I'm not going to get anything, right? If the microcontroller only has 3.3 volt output. Let's try that again. So it's, yeah, this light comes on first, and then that one comes on. And if we go all the way up to 7.3 volts or so, it's on full brightness. Unfortunately, the video camera is adjusting the brightness as I move over there, but you can see that it's definitely changing based on what I'm turning here. There we go. Alright, so that seems to work, although it seems like the range of control is not as wide in the 10 volt range as I thought, so you have to start from 2.6 or whatever that was, 4. Seems like this light doesn't turn on until 4, and then yeah, so you've only got about maybe 5 or 6 volts is the actual range of control, seems like, not really 10, so that 0 to 10 there, it's not really the full range of control, is it? Okay, now I'm just experimenting with different voltages on the solid state relay. So 5.5 volts, for example, on the input side, we get a slope of, what does it say there, 0.6 seconds approximately? I mean 0.6 degrees per second. It's a little bit up and down, but I think 0.6 is what it will settle at there. And you can see from the red line there, I've been changing the slope of it a little bit up and down as it goes, so I can control it fairly nicely within whatever range it can run at. And unfortunately, it doesn't turn on until a minimum of what was it? 4 volts. We need 4 volts on here before it even starts to do anything. So yeah, it's not as controllable as I'd hoped, but looks like for at least this middle part of the range we should be able to follow the blue line quite well. So if I twiddle with the dial a bit while it's running, I can get it to roughly follow the blue line like that, but I'm starting to wonder if it's really worth even bothering trying to do that. Okay, I changed the battery that I was using to supply the potentiometer with power for the SSR, and it's a 3-cell battery now, so that lets me actually get to the full 10 volts that the SSR can use as the range. And playing around with that, I was able to get a slightly better result because it can rise a bit quicker. So that's what we've got there, and I'm starting to think that this whole PID idea just really not necessary, because all I needed to do for this was start it. Basically, I started it at full for the first part, and then I hit the start button over there at just the right time so that the slope would meet at the first corner of the blue bit there. And then I just turned it off completely and waited until the red line rounded out to about the same slope. And then I set it to 5 volts on the SSR input, waited to here, and then I put it to full again, and it climbed, or waited to slightly before there actually, and then put it to full for this last climb and then turned it off. So I'm really only making 3 adjustments, and once you've figured out what times those adjustments need to happen at, that's all you need to do really. You don't need to have PID loops or anything like that. You can just set up, at this time set the voltage to this, at that time set the voltage to this, at that time turn it off and turn the fan on, of course, and that's it. So yeah, I've seen a lot of people using PID loops for this, but I'm just starting to think maybe it's not necessary, and this whole app could have been a little bit simpler. Although I do like the graph that I've made, that's pretty cool, and so I'm thinking now maybe I'll set up a different sort of a configuration. So my configuration here, if I can just push that, so you set it up like this to be ramping up to 100 degrees over 30 seconds, for example. Or I was also thinking to have a constant temperature. It's a little bit tricky with the touch screen here, but can we get that please? Or you could just have a constant temperature like that if you wanted to run it as a coffee warmer or something like that. But anyway, I think I'm going to finish this video here because I've been working on this all week, and quite frankly I'm kind of getting sick of looking at it. Plus it is functional enough now. Like I did a little bit more experimentation with my sample board here, put some smaller parts on and some larger parts, and everything seems to be working perfectly fine. So as far as using it in real world situations goes, it should be perfectly functional. And what I'm thinking I'll do is I'll just set up some sort of a timed sequence like I just mentioned, and then I'll make it turn on a buzzer just in case I'm not looking at it carefully enough. When the buzzer goes, I'll just have another sort of a table here, probably not wood. Wood would be the easiest thing to make it from, but ideally I think it would be something like this sort of ceramic that's not going to be the two conductive heat conductive one way or the other. And so just sort of push the board off sideways like that, and keep it in the same area that the floor fan will be able to cool both this and that down. And that will give me about a 10-minute turnaround time on this, which is probably quicker than I need anyway. It's not really like I'm going to be making a bunch of boards every 10 minutes that can go on here. Maybe, I don't know, that would be nice if one day I could do that. But anyway, so I'm just going to push it off like that, and that will be good enough, I think. So that kind of makes me not really want to work on this software too much more. But like I say, it's quite good. I think I'll put this on GitHub anyway, maybe not right away as you're watching this video, if you're watching the video the day it comes out, but within a day or two after the video goes up, I'll put this up on GitHub. Although just keep in mind, there's no connection between the inputs and the outputs. So there's no PID loop or anything, because obviously I didn't really get to that point. But if you want to play around with it a bit, there's settings here. This dialog here has this section here, output overrides. So those 3 checkboxes will turn on the 3 digital pins. I'm not sure which ones they are, but 3 digital pins somewhere in the middle, just where the Raspberry Pi logo is there, will turn on with those checkboxes as an override. And the PWM percent, if we put that slider up, you can actually see quite a good touchscreen. This one is quite responsive. But so those values over there are the live values that those pins are actually outputting. And for example, if I turn cooling on here, you can see cooling goes on, and one of those pins there will have just gone high. And if we make this PWM slider go, where are we there? We slide this like that, so that it's over there, that goes up to 33% or whatever it is. So that PWM pin is being output to 33% duty cycle there now. But there's no connection between those outputs and the thermocouple input. So you'll have to code that yourself, I guess. But I'll put some comments in the code, or maybe I'll put some description in the GitHub repo README about where you would need to look if you want to connect those inputs and those outputs. And these outputs are only being overridden here while this dialog is open. So as soon as I close that, so we've got 33% there, but if I close this, then everything just gets set back to zero as soon as that dialog goes away. Anyway, yeah. So it wasn't quite the success that I'd hoped for, but it is kind of functional still, so I'll see how it goes. And instead of trying to make a fancy finished product sort of thing like this, I'll just start using the thing for what I actually need to use it, and when I find problems, I'll fix them as I go instead of trying to fix everything up front. Anyway, thanks for watching. See you later.